โอเคก็9:10 นาทีเริ่มนะฮะ Well then good morning so today we're gonna continue our lectures on instruction set architectures. Let's see if I can get this stuff here. Okay, that should work. Yeah. All right, so before we continue, let me recap the idea from last week. Toward the end of last week lectures, we talked about memory alignment. No, we talk about endian or byte order. The idea is that you have big data, kind of data that span across one byte, but now you have to use multiple bytes to store data. What should be the proper order? If I don't like this setup anyway. All right, we'll continue with this. No. Okay, fix that later. All right, if you have data that span across a byte, like you have big number like this, 1A, 2B, 3C, 4D. You have two choices. First choice, you write the high precisions, high order at the lower address. Okay, higher precision at lower address. That way, if we read from lower to higher, the first byte that you read would be the high order byte. Okay. Another idea is you put lower order, lower precisions at lower address. Similar things, if we read from low to high, that means the first byte that you get would be the low order byte. Okay, let me explain this in Thai for those of you who might have trouble with it, so that you got a clear explanation of it. จินตนาการคุณมีเลขหลักหน่วยหลักสิบหลักร้อยนะครับหลักหน่วยหลักสิบหลักร้อยบังเอิญด้วย common sense ของเราที่เราเรียนเลขอาราบิกเลขอาราบิกก็บอกเอานัยยะสำคัญต่ำไว้ที่ทางขวามือแล้วนัยยะสำคัญสูงนะครับ low high นัยยะสำคัญสูงไว้ทางซ้ายมือตอนเราบวกเลขสมมติเรามีเลขสองจำนวนเราก็บวกจากขวาไปซ้ายนี่คือระบบอาราบิกขวาไปซ้ายแต่จริงๆแล้วในคอมพิวเตอร์ไอ้คำว่าขวาซ้ายเนี่ยมันบอกด้วยตำแหน่งนี่เบอร์ศูนย์เบอร์หนึ่งเบอร์สองอะไรเงี้ยครับประมาณนี้เนี่ยคุณเขียนเบอร์ศูนย์เบอร์หนึ่งเบอร์สองอย่างนี้หรือคุณเขียนเบอร์ศูนย์เบอร์หนึ่งเบอร์สองอย่างนี้ คือไล่ตำแหน่งมันยังไงนะครับ แล้วก็ถ้าเกิดว่าคอมพิวเตอร์สมัยเก่าๆเราบอกเราอ่านจากตำแหน่งต่ำเป็นตำแหน่งสูงดังนั้นถ้าเกิดคุณอ่านเลขใหญ่ๆใบแรกที่คุณอ่านมันเป็นนัยยะสำคัญสูงหรือนัยยะสำคัญต่ำ okay this is how to explain it with base 10 number that you may be more familiar with it maybe you more familiar with it all right so that's the Indian things and we got several examples like okay if you start with if you use little Indian means you read from lower first you start from low and you keep continuing it's like the way you do with the Arabic number that you use but if you do the big Indian you read the high order byte first it's better for comparison because you read the first byte you know which one is bigger simple okay เหมือนคุณอ่านครั้งแรกคุณอ่านหลักพันหรืออ่านครั้งแรกคุณอ่านหลักหน่วย okay that's one way to think about it yep that's the Indian things this is one decision that architects have to decide how would we order our number our data in the memory in the big memory okay this wouldn't be a problem if your data is just 1 byte it doesn't matter right it only matter when we have data that is bigger than a byte so you need multiple bytes how would you write it in order like that and then we talk about memory alignment again this is from historic reason we say oh you put out an address you get a byte of data this is 8-bit 1 byte I give you an address you give me 1 byte of data but as the technology improve we say what if I give you an address you give me a row of data and a row can be 2 bytes 4 bytes or 8 bytes so the address becomes the row all right that way we can read faster it's like okay let me give you a real example here if our door only allow 1 person to get in at a time it's like this picture 1 at a time 1 read you get only 1 person coming through the door but what if we decide that oh we want to make it faster so we extend the door in a way that now 2 persons can get in at the same time 2 persons at a time okay now 2 persons can get in that means when I say I want row number 1 I get 2 persons I want row number 2 I get 2 persons and if our data kind of align within the same row that's easy but if our data is like this okay I change the color green that means to get my data I have to read 2 rows and combine them together meaning slow got my point and nowadays yes please this is 1 byte 1 block 1 small block is 1 byte the number in there is the address okay and modern architectures we have what we have 64-bit architecture 64-bit how many bytes 1 byte got 8 bits So 64-bit is 8 bytes. So it would, if I have to draw a picture, it would be like this. We got a processor and we got what? 8 rows at a time. So it's like I extend the door now, 8 people can get in. So alignment become more important. Okay. And we call the architecture that only allow you to put the byte within the same row, the bytes within the same row as restricted alignment. Restricted alignment. That means if you have 16-bit number, you must, okay, put them in the same row. It may sound a little strange at the beginning, but we still do byte addressing. What does it mean? Byte 0 is here, byte 1 is here, byte 2 is here, byte 3 is here, byte number 3 is here, number 4, number 5 is here. So it's kind of odd and even. In this case. And when I say I want the first row, I would say number 0, but I got actually 0 and 1. And when I specify I want number 2, I actually got 2 bytes, 2 and 3. So we use the byte addressing, but read a row of data. And a row can be 2 bytes, 4 bytes, 8 bytes, depends on the architectural design.
Does this mean that the size has to be like a certain infrastructure? For example, can it be like, because like the alignment wouldn't make sense if you have, for example, both size 2 or size 3, right?
Well, think about it. If you think about it, the number of bytes that you can read would always be a multiple of 2. So it would be 1, 2, 4, 8, like that. So you can just do restrict alignment by just mod the starting address with the size of the data. That way you get the proper alignment. You got my point?
You have to know the size before.
You have to know the size of variable, like you have to know that, oh, double would be 16-bit.
Okay, so you have to use the biggest size to as well.
This is 16-bit. If you have what? If you have character, that would be 1 byte. So that means you can put it anywhere. But if you have integer, that would be 16 byte. That means you have to put it like this.
So we have, like, for example, we have size 2, size 4, size 2, we should use size.
Size means size of the variable, not size of the bus, not size of the data, not size of the gate, size of the data. Okay, better? And this is just the comparison. If your architectures decide to go with unrestricted alignment for whatever reason, usually for compatibility reasons, it means you can write simple software. But sometimes it's slow because now I read data, I may have to read multiple times and reconstruct the data inside the processor before perform any calculation. So modern architecture would not go with this. They would go with restricted alignment, which is faster. Okay, and we got a case that the architecture itself doesn't enforce restricted alignment, like Intel. Intel doesn't enforce restricted alignment because historically all software doesn't do restricted alignment. But if you want better performance, you can perform alignment by yourself, and it is faster. It will be faster. Got my point? And real example is like this. When Mac still use Intel processor, same software running on Windows or Linux, will use less memory because it doesn't do restricted alignment. But when Mac decide to use Intel processor, since Mac doesn't have legacy code, old code, so Mac compile everything to be restricted alignment and faster. So same software running on Mac, faster because Mac compiler now do automatic alignment. Okay, so technically speaking, alignment is better in terms of performance. And now memory is so cheap, so who cares? All right. And yeah, just write down here. Burden is now on software or on compiler, but for performance, let's do it. Okay. And another things that I want to recap, addressing more. Okay. Let me recap this idea again because some of you may not familiar with the low-level assembly code. All right. It's like this. When you say A equals something, maybe in Java, in Python, actually, you want to be able to specify a constant number. I want number 4 in my program. So I can just write 4, and when I say write 4, actually it would translate to binary like this, right? That would be number 4 in binary. So when we say load R1 with number 4, it would translate to just quick makeup of this, something like this. Number 4 and register number 1 like this, and the opcode for the load, which would be some number anyway. So every instruction would translate into binary like this. Okay, and if some bits represent constant number, we call that immediate. Yeah. You can guess from the name. Immediately use this value. That's from the name. All right, that's for immediate. And if the operand that you specify happen to be registers all the way, we call that register direct. That means every bit that we write down represent the register, the internal memory of the processor. That's register direct. But in real world, immediate and register direct, is that enough? No. We also know that sometimes we use index or offset. In this case, we call it displacement. What is displacement? Think about it when you have an array like this, and you say you want D100. That's displacement, meaning from the beginning of D, add 100 to it and get the data from it. You know my point? Translate into just memory. Okay, maybe I recap this a little bit for you. If I draw this data structure into a memory, it would be like this. Let's say I got, each row got 4 bytes. To simplify that. We got what? ABC. ABC would go like this. A, B, C, because it's just 1 byte. Right? And we would got D and hundreds of it for D. Right? And we would got what? E, 200 of it. So technically speaking, when you declare variables, you just allocate memory. Like you say D 200, that means, oh, I want 200 bytes, and I would call this 200 byte D. So when you want to read inside this variable, it's just, oh, this is the beginning of D. I want D 100, that means add from the beginning with number 100. Get that data for me. So everything translates into just address. That's why we call addressing mode. Your variable is simply data in the memory. That means to reference to it, you need an address. Down in the computer, they have no notions of A, B, C, D, E, F in this case. They just give me the address, I give you the data. So you write software, you say D100, that's actually translated into, oh, to get the address of D100, it actually add 100 to the base address, in this case, in register R2, equivalent to D, just an example in there. That's we call addressing mode. How to translate from variable into actual or physical address to get your data. Right? If you think about it a little bit, that's pretty straightforward. It's like you have a book, you have a notebook. They have no idea, oh, this first line is for A, second line for B. No, you just make it up in your software. From the notebook point of view, it's just, oh, first line would be low 0, second line would be low number 1, right? So if you want to read the first line, you may say read A, but the computer would say, I would read line 0. Right? If you think about it a little bit, just direct translation. It is straightforward. So displacement means you add 100 to the base address and get it. And that's also true for data structures. Or in your case, you may be familiar with the word object. You know object, right? Object means one big variable with so many property or small variable inside. That's object.
Or you can just be 100, not be 0, 100.
Say that again.
It starts 200, it takes 200.
It's 0 to 99, 199. The size is 200, but the first data would be E0, right? And you only add 99, 199 to get the last data. See, you add the data. That's why we always start with index number 0, mean add 0 to it. Okay, so that's displacement. Add some number to the base address. And similar concept, register indirect mean you calculate the absolute address first and read from that address. Like that, straightforward. Index mean both base address and index are variables. So you have to add them to get the absolute address. That's why we call it index. And for direct, basically mean you hard code the address. you hard code the address, you specify the address. So this only makes sense if you use memory map IO or do embedded programming. Oh, I put device at the address 1000, so I read the device from address 1000. Okay. And scale means you do some calculation before you add it to the base address. And you can just follow the example for delays. And again, before the end of last lecture, I asked you this question. What kind of addressing mode do we really need? Still remember the answer? What do we really need? Mean you must have it. And what can be ignored? Meaning you can use other modes for that to replace it. So I would say we need immediate. And what else? We need register indirect and register direct. I would say if you got these three modes, that pretty much you can do anything. But with good performance or not, maybe not. Why? Because that means if you want to do something like displacements, you have to add them manually first and then use indirect addressing mode. Meaning it would be slower, right? Because with displacement, I can say, I want 100 bytes from that, get it for me within one instructions. But if my processor doesn't support displacement, what does it mean? Oh, I want some data, but it's 100 bytes from the beginning, so I add 100 to the beginning. That's one instruction. Second instruction, use the result as an address and get the data for me, right? Two instructions. But if our processor support displacement, wow, I just say, I want 100 bytes from this, they get it from me right away. Okay, are we good? I try to slow down and make sure you understand it. Okay, so how to answer what kind of addressing mode do we actually need? Maybe we do some experiment, right? And that's this slide. Okay, let's take software or benchmark in this case. Get the real software that people use and see which addressing mode that we frequently use. We may learn that, oh, people use memory direct, not that much. Scale, well, not that much, but wait, displacement, immediate and register indirect, they're trying to use it. So as an architect, you would say this is the function that people like to use. We should do it. And more than that, make it faster. According to Amdahl law. Okay, now you may get the rhythm. When we want to design something, we say, what do we want to use? Oh, this is the function that we want. Okay, make it happen. It's actually design principle, right? What do we want? What kind of instruction that we want? What kind of addressing mode that we want? We want to use this. We like to use it. We frequently use it. Then use it. Make it. โอเคทันไหมน็อกไปละพยายามไปช้าๆไม่รู้ ทำให้หนักกว่าเดิมเปล่า Okay now here's the question in itself let me get back to this I say whatever instruction that you write it would get translated into bunch of bits right so it's like I say load number 4 into R1 we have to somehow specify number 4 we have to somehow specify register R1 we have to somehow specify the instruction load everything in binary just 0 and 1 The question is if people say we like immediate that means we have to dedicate some bits for the immediate right how many bits should we dedicate them for immediate number again how to answer that let's do some experiment what would be the size of immediate that people tend to use see the rhythm of it same thing oh people like to use displacement eventually it would translate to I don't know right the number 100 have to be here 100 here something and the register R2 have to be specified somewhere right so how many bits should be dedicated for the immediate sorry the displacement let's do the experiment okay and I got the experiment down here for you this is for immediate this is for the displacement again we use real software real benchmark and let's count how many bits should we dedicate them for immediate and we say oh usually people use no more than 8 bits or sometimes 16 bits for integer value you may think about it when you say a equals something how big is that number if it's just 1 2 3 4 okay right? If you got 4, you need what? 3 bits to specify number 4. If you say A equal 10, how many bits do you need? 4 bits. If you say equal 100, how many bits do we need? About 7 bits, 6 bits, right? So from this experiment, we would say maybe 16 bit is enough for general use case. Just do the 16 bits. Same thing when you say A something. How big is that number? That's for the displacement, right? You say A100, A200, A6000, maybe? I don't know. But the experiment show that usually we use A0, A1, or up to no more than 16 bit, which would give you about 64K. In some programming language, you cannot declare an array larger than 64K because they only allow 16 bits of index or displacement. That's no longer true anyway. ไหวไหมทันไหมผมสนุกกับวิชานี้มากเลยตั้งแต่ไหนแต่ไรแต่เวลาสอนเนี่ยพวกคุณนั่งอึ้งกันทั้งห้องทุกที เวลาสอนเด็กวิศวกรรมจะดีกว่านิดนึงเพราะเรียน logic design เรียน low level hardware มาหน่อยนึงก็จะคุยกันง่ายหน่อยสอนเด็ก ICE เนี่ยพาร์ทเนี่ยจะนั่งอึ้งอยู่ในห้องทุกเทอมอะไรมาเนี่ยผมเข้าใจพวกคุณ we good still good okay all right that's how we come up with problem so from this we would say 16-bit for displacement and 16-bit for immediate okay now what kind of instruction do we need when you write software what operation that you use well usually we have to move data around like move from one register to another registers you have to load it from the memory or store it back we call those instruction data transfer or data movement what else do we write software for arithmetic right you do what add minus multiply divide we got more than that modulo what else you usually write square root maybe not you usually use trigonometry function maybe not what else again we cannot implement every single mathematical operations into the processor that would be too expensive right then we have to select what kind of operation do we need do we need square or power no. Why not because you can just loop with multiply right like if I say I want a to the fifth I can just multiply 5 times right so maybe we don't need square operations for example anyway those math function operation we would call them arithmetic instructions so architect have to decide what kind of math operation should be put in our processor what else logic operation what is logic then you know and you know or you know complement or not you know them yeah I would guess that you should get familiar with something like this right the gate right yes still have idea we can also program that in the processor so most processor will support basic logic operation and or exclusive or complement or not but again which one should include well it depends on the architects and usually architect would what Okay, which operation that people want to use, then we implement that. What else? Control instructions. What is control instruction then? Any instruction that means next instruction would not be the adjacent one. Or you may familiar with if, else, go to, something like that. Go to, jump to that address. Or call and return.
That like give like a follow to jump to other instruction.
Right. So that's control instruction. In a sense, where is the next instruction? If it's the adjacent one, the one next to you, no need. But you got if else, if this is true, go there. If this is false, do this. If this is true, do that. See, we got condition. That's why we call it control instruction. Based on this condition, make a decision where to do, what to do next. It is straightforward. What can you do in your programming language? Python, whatever. Same thing. We need that in low-level machine. Right? And apart from that, we would have the extended instruction. We have the extended instruction. What is extended instructions? Well, some processor may say, oh, I want my processor to be able to decode MP3 music faster. So I include some kind of vector functions to allow me to decode large data. We usually call that extension. Or I want to be able to perform encryption faster. Include the encryption function. Okay. And I want to focus a little bit on the control instruction. If else, so let me change the colors. Okay, move here. It's like this. You got an if, right? What would you put inside the if? Usually when you do if, it would be A more than B, right? Or you put what? A less than equal to B. C is kind of inverse, right? One if is another thing else, right? Or you may put in A less than B. And you can do what? A is more than or equal to B. Or you can say A equal B. That would be the opposite of A not equal B. So what kind of operation that you put in the comparison here? What? Not get, not really, but yeah, that's possible. So question is, when you do the if, you do if equals, that would be A equal B, right? And our stats show that people usually go with equal rather than not equal. So maybe we should support equal. And if they want not equal, go with the else. Okay. Same thing. You do A is greater or equal to B, or you do A is greater than B, that show that people usually go with more than or equal to. And people like to use less than or equal to and less than. Right? It's from the stat anyway, statistics. So, as an architect, which condition you want to implement into the processor? We can just go with equals. What else? Less than or equals and less than. And you can ignore the others, right? Because they're just the else of these three. See, you don't have to implement everything into the processor. But we want to implement something that would be minimal but useful and sufficient. To get that minimal, useful, sufficient, do the analysis. Okay, we good? And anyway, this is jump or go to. This is call and return, and this is if, basically, conditional branch. Low level machine, we do not call it if, else, we call it conditional branch. Same things. Okay. So it's like this. If you write, let me give you a specific example because you may not familiar with assembly language. If you write, if A equal B, then do something, and else do something, it's like that. If you translate this into assembly, it would be like this. B branch, B for branch anyway. And usually it would be BEQ, branch if equals. That should be R1 for A and R2 for B and go to somewhere. Like that. That for the assembly, when you say if, it translates into branch if equal. Anyway, you would see that in as we move along, we see more example like this. But since we talk about low level machine, so you do not see if else, you do not see A, B, you just see bunch of address, bunch of instruction. Right? Same questions. When we say go to or jump, how far do we go? To answer that, we also do statistical analysis. We see that, oh, maybe 16-bit is enough. People do not want to go that far from the code. All right. Anyway, well, kind of a trick question, but not a trick question. Okay, let me ask you then. We usually branch at displacement, but okay, I skip that for now. We get back to that later. Let me explain again displacement. All right, let's try this example. I say if equals, when you write the assembly, you would see BEQ, branch if equal, and go back to the loop up here. It's like a while loop. Do something, Y, A equals 0, something like that. Branch if equals. So I do something, then at the end of the while loop, it's like branch if equal, if it's not 0, let's go back and do the loop again. Okay. This is the C code, this is the equivalent assembly code on the right hand side. But when we get translated into the machine code, the loop would get into relative number, like, oh, it's 120 bytes from current point. The question is, why most architecture would go with relative address of displacement? PC for program counter. Meaning if you are now working on this instruction, the program counter would be here. And when we say go back, rather than say go back to line number 5, we will say go back 4 lines from this point relative to my lines. Why? You got it? No. Too fast? Too many informations? Okay, let me try to explain it a little bit more details. It's like this. Oh, I got line number 1 and address, okay? I do something, maybe A plus B, C equal A plus B, okay? Line number 2, I do something, okay? Line number 3, I say, oh, if C not 0, go to number 1. All right? But rather than say go to number 1, most programming language or most computer architecture would say go to -2. That would also give you number 1 because now I am at line number 3. And I say go back 2 lines. That would give me number 1, right? The question is why most architecture prefer to use relative address, we call displacement, rather than absolute address, the real line number.
The real address might be like very long. Very
Okay, that's one possibility. The line number may be very long because if we use 64-bit architecture, the address would be 64-bit. That would be big number. And that makes sense. But else, when the address is small, we also prefer displacement. You got it. Anyway, that's one answer, one correct answer, but it's more than that. Yes. You got it, yes. Because in reality, I can move my software anywhere. And it may be number 10, number 11. Let me change that. Number 11 or number 12 or number 13. If I say go to number 1, wait, number 1 is whose code, not my code. But if I say go back 2 lines, it's always relative to my code. That would be my space. You got my point? When you write software, you assume that you start at line number 1. Your address is number 1. But in reality, you may load your software somewhere else. You can load it at number 1000. So if you put in absolute address, you would get wrong address. There's a word for it, we call it relocatable program, meaning your program can load at any address. What?
So this is like going to step back.
Go back, yes. And if you go forward, like go down here, rather than go to number 6, you would say what? Go to +3, right? To go to number 6. So that's one concept, actually, relocatable program, relocatable software. So computer guy would prefer displacement or relative address because now it's relocatable. It can be loaded anywhere. It doesn't have to start at 1, or it can be start at 12, 25, and still work correctly. Okay, what if the examination asks you, what is relocatable program? This is one answer for you. Or they may ask you the opposite. Why would we prefer relative address or displacement rather than the absolute address? That's one possible answer. We want our software to be relocatable. Again, we got 2 professors for this class, right? For this course, not this class, for this course. So we didn't say yet who will do the exam for which part. So I don't know. I have to teach you everything. Make sure that if another professor would do the examination sheet, you can answer that. Just have to make sure that. Or if I make question for this part, you can answer it. Just to confirm, this is mandatory class. Right? You cannot drop, right? If you drop, you have to see me again next year, right? Okay. So you got no choice but to stay with me. And either love me or hate me, and you have to stay with me. Okay. So about the addressing mode, new processor would support displacement, immediate, register, indirect, at least, right? From our statistical analysis. And they would have 12 to 16 bits of displacement and 8 to 16 bits of immediate field. For complex addressing mode, let's the compiler do it. This is the building block for that. So you will have to design minimal processor. This is the addressing mode that we really need. Okay. Any question about the addressing mode? Okay, be good. Let's move on to the topics of subroutine of functions. Subroutine of function. You may know it as call and return. So what is call and what is return? Call, you mean you call other functions or other procedure or other subroutine, depending on programming language that you're talking about. They may have different name for it. But you may be common function that you want to use a function and you call it, right? You can reuse the function. So how would you call a function? If you write it maybe in Python, okay, let's try that in Python. Okay, you would define a function def add, right? And you got what? A, B. Okay. You know Python, right? You read Python, right? And you may do something like this. Return A plus B. Okay. Make it simple like that. Mm-hmm. Def, so define a function in Python, right? Anyway, I don't like writing on the iPad, but it's better than the stylus anyway. So and I don't want to carry my stylus. Oh, return, right? I missed an N, sorry. A friend of mine told me that my handwriting looked like a doctor, I mean the physicians. And I say, no, I'm much better. And my friend that happened to be a physician said, no. He said, I can be a doctor from my handwriting. I say, oh, no, that's not a compliment. I don't like that. Okay. And when you want to use it, how? Let's say you want to do add. Okay, let's make this a little real here. C equal add 5 and 2. Okay, you will do something like this, right? In Python. Let me translate this into assembly. So you understand what happens. Okay, change color to red. So add would be like, we got the label for add. Okay, and it may do something like add R3 R1 and R2. Okay, just make up something here. And return in assembly. Okay, in assembly. So the red is the assembly. Okay. All right. Now you want to call add. How? You have to load what? Load R1 with what? Number 5. Right? Load what? R2 with number 2. Right? Then you call add. And you got the result in C, assuming that you would use R3 for C. Or if not, you have to move anyway. Okay, let's assume that R3 would be your C to make it simple. This is function call in assembly. Yeah. So everything that you write in Python, in C, in Java, it would translate to machine code like this. Pass to the processor. The processor would do calculation for you. And just make up simple software, simple code, okay, to make it easy to understand. Real things compiler would do much more complex tasks for you. Yes, please.
Where the define part of it, when we define it, we're going to use the add. That's the data has to be how or can be specified.
Aha, that's my question. Yes, you got the point. The point is, wait, this add function use R1 and R2. What if I also use R1 for other thing else or R2 for other thing else? It would be conflict. So this code is incomplete because actually you would have to save R1 and R2 first because you know that the add function would use it. Right? You have to save R1 and R2 or else you get into trouble.
So some machine is saving the form of the
it's either the subroutine save it for you or you, the caller, save it. In the next slide anyway. Next few slide. Right. We have to save it. We have to save it somehow. Map this concept to your programming language class. You would learn about local variable and global variables, or variable scope anyway. But I didn't get to that yet. But yes, you mentioned it. Yes, good. Okay, let's stop here for now and see what really happens. This is what we see in the instructions. But what happened in the processor is much more than that. Okay, how? Because when we have the call instructions, we have the call instruction. What happened is that call what? Call add. Okay, and when we see the return instruction, return to what? Return here after the call. Right? I call mean jump here. Return mean jump here. Right? Okay. Are we on the same page? You good? When I make a call, mean jump here. Do this and then jump back here. Right? That means we need a place that would say, whenever we have a call, let's remember this. Let's remember this. Let's say this address is 5,000. So you have to put 5,000 somewhere. And when we have the return instruction, we see the return instruction, we read this number and put it back and continue. We call this the return address. Right? It's like I'm running instruction in order. Oh, this. Then what? Call to that function. That means I have to say that, oh, after finish that one, you have to come back here. So I save the address. I have to come back here, put it somewhere. Then jump to do that code, the add in this case. Do the add, once finished, return where? The address that I remember previously. In this case, it's here. Jump back. So you have to understand what is the return address. And in the processor, they somehow have to say where to store the return address. Intel decided that this would go to special place that they call stack memory. Stack, S-T-A-C-K, stack. Stack.
Why do you use stack?
Because stack got orders.
I just like how you stack text together.
Number. Stack. Okay, sorry. And this would work for nested call, right? Because if in add call something else, the return address would get on top. And when you return back in order. Right? It's like, oh, here I call your function call other function call other function. When you return, you have to return in order. So stack is the best place to store that because stack means last in, first out, right? Data structure. So Intel said we have a special place in memory for each process. We call it stack. You put it in stack. You use the term for stack, it would be push and pop. Push in, pop out. So we need return address. And we need parameter passing, which in this case, I show you, we use register as a parameter passing. But we also have to save current status, save the return address, and then call. So there are more details to that. This is the real example from Intel processor. Oh, not Intel. Example processor. I simplify it. So we got similar example, but now in C programming language. Okay. To pass parameter in this case, 5 and 4. You would have to load them and then call, same things. This one use register for parameter pass. This one decide to also use stack for parameter passing. That means, oh, we got 5 and 4 pushing, then call. This is Intel style anyway. Also pass parameter using stack. So again, there are two ways to pass the parameter to subroutine. First one, let's use registers. But now we have to define which register to pass the parameters. Or Intel say, no, let's go with stack. Since we already have stack for the return address, push it to the stack. And when we want to read, then we need some index from the stack to read the variables. Today we would have exercise number 1, assignment number 1 out, so you would learn more about this. No worry. Okay. Oh, that's the worry part that you can worry about later. Okay. You can review that later. If you think it's too much. And another question which your colleague just mentioned earlier. Now, what if my routine use R1 and the main program also use R1? That means now it's your R1s and my R1 are two different registers. We have to save it somewhere, right? We have two choices. We have two choices. First one, the caller. I will call you, so I save the variable. Make sure that when return, I can load it back. And another idea is the calling. I call you, so you have to make sure that once return, my data is still the same. Okay, let me give you an example here. Let's say I got a piece of paper. กระดาษทด I got piece of paper กระดาษทด and this has to share between me and everybody that do the work for me.
Why would you share here?
Because we got limited memory on the processor. Okay, and I say I use my line number 1 in my piece of paper for A, my A. Okay, when you use this paper, you also use line number 1, but you use it for X. Okay, when I pass the processing power to you, you use line number 1 for X. Okay, So I have to ask you to do something. And when return, I want to make sure that line number one is still my A. Got my point? We got one piece of paper that have to share with everybody. I write my number on the first line. I ask you to do some calculation for me. You say you also have to use the first line for the calculation. Same register anyway. Now I want to make sure that when you're done, you return that to me. I can continue to work on the first line with my number. How to preserve that? We have two choices. First one, caller. I mean, I call you, I ask you to do something. Then I know that, oh, I use line number one. I save it somewhere. I make a copy, write it down somewhere. Then I pass this paper to you. You finish your work, you return it to me. I put back my original value to line number one. And that's how it works. I push it somewhere else. When you return it to me, I pop it back.
And what about result?
That depends. Okay, we have to specify that all the result would always go through stack or to register, another register. That are the things.
So this is about the first introduction.
Okay,
Yes.
so that's caller save. Before I call you, I say I use line number one, so I have to preserve line number one. I push it somewhere else. You send it back to me. I pop it up.
And you put the result somewhere.
And the result may be somewhere else. I'll have to read it back. It can be that you do the side effect function for me, meaning I ask you to do something, you write to the screen. You don't have to return anything to me. That's also possible. Or second idea,
I save it.
you do something, make sure that when you return the paper to me, it's in the good condition. Calling save. Meaning I pass the paper to you. You say you want to use line number one. So you put it somewhere. You do your calculation. Before you finish, you put it back and return it to me. And it's here. See the point? So you may say, oh, it's somewhat similar. It's just who would do? But actually, one is better. Why?
One is better.
I would say more benefit, not always better, but more benefit in some cases. So it's caller or calling. Which one is better and why?
But I feel like caller is that function.
Okay, I'll let you think for a few seconds. Caller or calling said, which one is better? Why?
I would say it's caller because there might be multiple callings. Something on that line.
Okay, if you ask me, I would say I go with calling.
Yes.
Why? Because as a caller, I don't know which line in this paper you're gonna use. So to make sure that my paper would be the same, I have to set everything. Right? If I use 20 lines I have to save 20 lines. That would be a lot.
So.
But in reality, when I call you, you say you just use the first line. But I don't know which line you want to use. So as a caller, I have to save everything. If my paper got 20 lines, I have to save 20 lines.
But that's the all you have to say the model.
But as a colleague, you say you're gonna use the first line only. You save one,
Excellent.
right? You got my point? I got a piece of paper. I write 20 lines of my data on this piece of paper. I ask you to do something. Since it's the same processor, I have to pass this paper to you. Turn it over to you. You say you need some lines to do your work. One line is enough, so you decide to go with the first line. If you save just one line. If you ask me, I have to ask you to do something and I have to save it. I don't know how many lines you want. I have to save everything. That would be more expensive. And Intel got some kind of expensive instruction they call push out and pop out that would save everything. And that's slow. That's quite slow. And people don't like that. But again, Intel was designed for whatever reason. They decided to go with color save in the past. But it doesn't have to be that way. It's just notion for the operating system, how to call, how to return. Okay, maybe let's have a retro break. And we're gonna come back with exception. I give you 15 minutes break. Go refresh yourself a little bit. Exception is a little challenging. Mhm. Okay, so we. Okay. All right. My question to you. What is an exception? You do Python programming, right? So you have use try something and cache. Sorry, Python use what? Excerpt, right? Right? This is an exception. What is it? What is an exception? Some kind of error. Does it always have to be an error? Okay. So there are several ways to define the exception, but the one way to define is that it's unprogrammed control flow, meaning you do not expect that, but it might happen. But exception in real world is happen all the time. Okay, it happens all the time. It can be anything. Let me clarify that a little bit. It's like you divide some number. C equal A divided by B, for example. One exception is that what if B is 0? What happened? That means you cannot divide, right? If B becomes 0. That's one example of exception. You do something and it cannot. You ask the computer to do something that it cannot do. Okay, one example. But there are several things that we also call it exception, like from hardware. Another example is you try to read from something that's not there. You read from a memory that doesn't exist, or you do not have a permission to read it. Sometimes people call it illegal operation. You just cannot do it. There is nothing there that you can do. Something like that. Or sometimes we use exception as a way to tell the system to do specific thing for us. We call that a trap exception that created from your software. Let me give you one example of exceptions. When you type something on your keyboard or you click your mouse pointer, that's also exception. Because now your software have to stop and read the key or read the mouse. It's not part of your software, but the hardware do something and you just have to stop and check the hardware status. Okay? That's also exception. So we can say that we have exception from hardware or external to the processor, and exception from software, meaning caused by the software or the processor itself. Some book would use the term interrupt for exception that caused by hardware, and use the term trap for exception that caused by software. But for some reason, Intel prefer to call them interrupt. So Intel call everything interrupts, but they prefer to use internal interrupt or hardware interrupt. It's just different way of referring to the same things. So if I ask you, I would explicitly say it's software, trap, or hardware, or exception interrupt. What happened then when we got an interrupt? Your program is now doing something, then suddenly somebody typed the keyboard. You have to stop the program, read the keyboard. Why? Because if you cannot read the keyboard within that specific time, you cannot read the key. It might be too late, right? The people may release the key and you got nothing. So exception happen all the time, actually. Keyboard, mouse, pointer, what else? Actually, we got one exception that happened every second, the real-time clock, because you have to update the clock of your computer. So every second, the real-time clock would trigger and update the clock. So we have exception all the time. And if you think about it, it's like a subroutine, a special kind of subroutine. You type the keyboard, we stop your software. We save the processor status, and then we call this special routine that would leave the keyboard. Then we return back to your software and you continue using your software. Okay? That's exception. right? Good. The tricky part is here. Exception happens. You have to call a software. You have to call a routine. Where is that routine? You need somewhere to tell the processor, where is my exception routine? Well, we have special name for exception routine, we call it handler. So interrupt handler is a special routine that would call when exception occur. But where is that routine? There are three ways to say where is that handler, where is the routine. First, we call it vector table. Second, we call handler table, and the last one we call it fixed entry. Let's see how it works one by one. You usually have to choose one when you design a processor. Vector table, yes. Exception happens, like somebody plays a keyboard. Okay. The hardware would wire that whenever a keyboard placed it, whenever somebody plays the keyboard, we would call it exception number 2 or interrupt number 2, for example. If your hardware decide to go with vector table, that means, oh, if the address is like 4 bytes and the source for keyboard is number 2, so we would go to byte number 8, use that number as an address to the subroutine. So you have to put subroutine here and end with interrupt return. Like that. So somebody plays the keyboard, your processor would stop it, go to this table and say, oh, I will jump to address 4000. Once done with the 4000s, in this case, you see the ILET instruction. We go back to your code. You may call this handler table a driver. In this case, it's a keyboard driver. So that's why when you have a new device installed to your processor, you would need a driver, a device driver. Partly, it is the handler routine. Somebody plays the keyboard, what to do? Somebody plays the mouse, what to do? Okay. So first way, make a table. The processor would look inside the table to find the address of your routine and jump to execute that routine. Okay, so it's like this. It's like my program is like line 1, line 2, line 3, line 4. I say I have a special routine for reading the keyboard at address 4000. So I make a table and say, processor, should an interrupt happen? Look at this table. And I put number 4000 in this table. Somebody plays the keyboard, the processor would look at 4000 and jump and do that. Okay, that's vector table. Unless a processor say, no, we would not make a table. We would not put address inside the table, but we like to put code into the table, and they call it handler table. You see the different name, vector table and handler table. What is handler table then? Rather than you put the address, handler table say, let's put the code in. So let's say one routine, I give it 16 bytes. If interrupt is number 2, so I will jump to 32. But rather than being an address, this is the real routine, the real code. So why is this better then? Why would this handler table better than vector table?
And directly use.
I can directly use the code rather than do another jump, which would take longer time. But the downside is I cannot put that many code in this table. I would have maybe 4 entry, 4 instructions. That would be too small anyway. So eventually I may have to call somewhere else or jump somewhere else. Right? But it's faster for interrupt that I don't want to handle. Just return. Somebody plays a mouse, now I don't want to capture the mouse, just ignore it, return. I don't care. So you can ignore some exception. And that will be shorter, right? Unlike the vector table, you have to jump and then ignore. Now you can see, oh, nothing to do, done. Okay, that's one example. And last idea, we say, no, let the software do it. Let the software do it. How? I don't care whether the keyboard is presses or the real-time clock set an alarm or somebody click the mouse or you do divide by zeros. I would always jump, the processor would always jump to a fixed address. And then at address 1000, you might have to do something like if the source equal, I don't know, number 2, then you call keyboard driver, for example. So fixed entry means let the software do it. Some architecture decide to go this way. Let's ignore the vector table, let's ignore the handler table, just fix the entry and let the software do whatever it wants. Okay, which one is better? I don't know. Just a design decisions. And of course, Intel go with vector table for historical reasons. Modern processor, they like handler table or sometimes they go software solutions, fixed entry. Just design decision anyway, nothing special. But in the past, sometimes the examination may ask you, if you have to design only one, which one will you go? Vector or handler or fixed entry? You can answer anything, but you have to say why. Why would you prefer handler table? Why would you prefer fixed entry? Again, modern processor either go with either go with handle table or fixed entry. We don't like vector table because it's slow, just like that. Right? Now, last topic of this chapter, instruction format. Well, from instructions, addressing mode, register, open, and everything, we eventually have to translate to binary, to numbers, 1 and 0. Okay? How would you format each instruction then? There are two main ideas, actually three, but okay, two mains with one variables. First one, we say, if your instruction is small, write it small. If your instruction is large, use several bytes for that instructions. We call it variable length. Variable length. So instruction may go from 1 byte to, I don't know, maybe 32 bytes, maybe. Like small instruction, okay, 1 byte is enough, stay with that. Some instruction you have to specify complex addressing mode, so it would be several bytes, okay. Another idea say, no, instruction would always be like 4 bytes, for example. Whatever complexity of that instruction, I only give you 4 bytes. You cannot write instruction longer than that. And some instruction, some processor would have hybrid mode. In one mode, you would have 1 byte of instruction. In another mode, you may have 4 bytes of instruction, something like that. Have different mode for that. Let's see an example. So Intel say we use variable length instruction, meaning Intel instruction can go from 1 byte to several number of bytes, depending on the format or mode. So Intel instruction is quite complex, actually. Okay, you will see this when you do assignment, but you can use Mac M1, M2, or you use Intel. Either way, you just got similar concept but different result. And another idea, fix the length of the instructions. So we would have like maybe 3 formats in this case. In this example, I give you 3 formats. The R type, the I type, and the J type. They are fixed format. That means 6 bits for opcode, and this would specify the format. If the format is R type, you would got 3 fields for instruction, for operands, for registers. If you got I type, you would got 2 fields for register and 1 field for immediate. And you got J type, you just opcode and 26-bit for address. So the nice thing about fixed length is that I can always use same amount of time to read each instruction. Right? Unlike variable length, I read first byte of the instruction, but wait, my instruction is 32 bytes more, so I have to read 32 times more. But for fixed length, oh, I read 4 bytes, I always got an instruction. So it's much simpler, much more simple. And modern architecture would go with this fixed length. And it's actually architectural in the past that people say, oh, fixed length is better. Another say, oh, variable length is better. But it's like this. If you go back to the CPU time instruction, in CPU time function, you will see this. It's like this. It's like this. If your instruction design is variable length, that means you can design complex instruction. Likely, this would be small, right? And this would be value. This is for variable length. But if your processor go with fixed length, that means to do some operation, you have to use a lot of instruction. But this is constant, maybe number one. So this is for fixed length. So people then ask, which one is better? This is like in the 90s, where Intel and Linux processors keep fighting. Which one is faster? Which one is better? And the graph show that, oh, even though sometimes you use lots of instructions, let's see, lots of instruction, 2 times the instruction, but you use less cycle. You use far less cycle, so performance is much better. 1 means you gain nothing, right? Better than 1 means you have better performance. So this graph basically, this line in pink is the IC. This line in green is the CPI. And the times of 2, the CPU time is in blue here, this one. Just to show that, oh, fixed length is much better. So modern processor no longer go with variable length, too much trouble. They will go with fixed length. Okay. So you may see actually that, oh, why Apple is so much better in terms of battery when comparing to Intel. Also from this. Why mobile processor, the one on your smartphone device, none of them is Intel. Also from this. Okay. I'm not saying that Intel is bad in a way, but for historical reason, they keep the compatibility. So that's why in overall design, performance, and battery, it would not be better. But Intel win in sense of compatibility. Intel still good at that. Mhm. But in terms of performance and complexity, that's too complex. Okay. All right. Before we finish the chapter, there's one more thing that you should know, and usually nobody talk about it in the architecture class, but modern architecture also have to consider this compiler. Why? Because we no longer write assembly code nowadays. You would write C, Java, or Python and let the compiler do it for you, or the Python runtime do it for you. So we actually design processor for compiler in a sense. And compiler also have a lot of impact on the performance. So that's why we have to learn about it a little bit. In this case, instruction set should also allow compiler to make better code, to make faster code, or in this case, efficient code. There are few things that we expect from compiler. First one is correctness. Of course, you compile, you say A plus B, it should give you A plus B. All right. Speed of code and compile time should be fast. And give you some kind of debug abilities. So what is good architecture to the compiler then? Or what can the compiler do? So I will quickly walk you through what the compiler can do for you a little bit. So when you compile software, either you have C, C++, whatever programming languages, nowadays they will translate to something that they call intermediate code. Okay, intermediate code, I write it down here actually. And they would do some kind of optimizations here. And at the end, do code generator to the machine code. So there are several things that compiler can do in this step. We got high-level optimization and global optimization. And in case you don't know, we got free compiler that we call GCC, GNU Compiler Collections, actually. Actually, the GNU compiler can do several languages like Fortran, C, C++, Java, several languages. The difference is that the front end of GCC would translate to different languages. So they translate different languages to the same immediate code, intermediate code. And Apple also got special compiler that they call, some people pronounce it Clang. I prefer to call it C-Lang anyway. That would compile it to special kind of intermediate code, they call it LLM. Low-level machine code, which is designed for optimization anyway. Just some word, nothing special about it. Let's take a look at the optimization. Maybe we learn how the compiler do and see that, oh, with this kind of architecture, we can actually do something better. Okay. Let's try high-level optimization. Okay. Well, usually compiler is good when you have a code that only one entry and only one end. We call this a basic block. Okay, this is compiler term anyway. Meaning if you have if else, if you have branch, if you have call, you have jump, that would stop the basic block. So compiler is good with the basic block. But if you have several basic block or too small a basic block, it's bad. So basic block is a code with only one entry and one exit at the end, like that. High level optimization, sometimes they just trash the basic block and put it in. We call it inline. Okay, let me give you a specific example. Maybe down here. Oh, okay. Inline is like this. Let's say I got in add a in and sorry, let me create a screen right again. Okay. In add in A in B. Okay. And you just return A plus B. Okay, if I got a sample code like this, and I keep calling add to add several add, you will see that each add would translate into what? Push, call, right? Each add would translate into push, call, push, call. That's so expensive, right? And one I call add, I just do only one instruction and then return. So every call to add would extend to what? 5 instructions. So expensive. I just call add, but it translates into 5 instructions in machine code. So expensive. So I just say, make it inline. In C programming language, you just put inline. And what inline happens is that rather than extend the code like this, it would put the assembly of the add instruction like here. So each call to add, just one add in machine code. One add, same as the one that you use here. You got my point? And you look confusing. Okay. Let's do this. I say, I call add, mean I ask you to do something for me. Okay, I call, hey, add 5 and 2 for me. So I ask you to do for me, I make a function call, I pass my temporary node, the piece of error to you. You do the add and you pass it back to me. I said by passing it back and forth, I need 5 cycles. So expensive. But in reality, what I just got is that when I ask you to do something, you only do one instruction. So I tell the compiler, rather than call you, move you to work for me here, so I don't have to call you. Put your code here. So I don't have to waste 5 cycles, call you, and you return it back to me. I just need 1 cycle and you work here for me. Okay, that's analogy of it inline. So if you just do inline, you got much better performance. In fact, compiler can also do that for you. And local optimization and global optimization is basically similar, but different scope. Okay, let me show you some kind of local optimization. What time is it? Okay, let's try this copy propagation. Okay, I show you this code. I got m equals 60, h equal m times 60, basically 60 minutes. 1 hour got 60 minutes, right? And 1 day got 24 hours. I got a seconds, number of seconds. So translate it into a day, divide by d. There is nothing wrong with this code, but to calculate this code, you need what? load, multiply, then divide. Wow, 4 instructions. Right? But wait, I didn't use M, S, and D for something else, for anything else. So why don't we just do the calculation by hand? And this would translate into just 1 instruction. Way faster. On my point? What I want just translate seconds today, number of seconds to number of days. But the code on the top, I need 4 cycles or 4 instructions, more than 4 cycles actually. Right? By do the optimizations, pre-compute the consent basically. I can do it in 1 instruction. Which one is faster? Of course. You see it. This is something that smart compiler can do for you. Or if the compiler is not that smart, you have to be smarter and do the optimization by yourself. Similar things, they can do common expression elimination, like if you see in this example, we got B plus C that commonly used. Right? So rather than do add B, C and add D, okay, X, B, C, X, D, okay, like that. Right? And what? Add Y, B, C, add Y, Y, E, for example. This would be 4 instructions. I can translate that to 3 instructions and it give me the same result. Got my point? This is also what compiler can do for you. Since we always use B plus C in both statements, so why don't we pre-compute B plus C and reuse it? See, little coding, little optimization, little moving, it helps a lot in terms of performance. Well, we got about what, 25% in this class? I'm quickly cut from my eyes. And how many students again? Should be what, 30, 40? Okay, never mind. Just do some helping. So I just hope that people that do not show up in the class, they would catch up on the videos and can do the assignment and examination anyway. All right, this is examples of what compiler can do for you. And good compiler can go from slow code like this to pretty fast code like this, optimizations. So even though you no longer write assembly, you can still write good code that would allow compiler to make fast code for you. Okay. Anyway, that's just quick idea about what compiler can do. At the end of the day, we should make common case fast. Okay. That means use the operation that you do a lot, make it fast. Mhm. And good instruction set architecture from the compiler point of view is that it should simplify the optimization, should provide primitive and allow you to compile program faster. Okay, just some buzzword anyway. Okay, and that's conclude the chapter.
So this is the exercise.
What?
So this is the exercise.
We got exercise here. Few more exercise. Not assignment. You would got the assignment from MCV, my husband.
Is it hard?
Is it hard? If you ask me, I would say easy because I can do it in few minutes. But of course, I make the exercise, so I can do it. Yes.
Choice essay written or what?
Some experiment. You just write code, do the timers, and do the analysis.
Well, right code.
I will give you the code. I show you later anyway. I give you the code, you compile it, run it, and do the analysis.
Oh. Okay. Sure.
Okay, I got few exercise anyway. Let's take a quick look and before we look at the assignment. Okay. We learn a little bit about compiler. We learn a little bit about instruction set, operation, operand, addressing mode so far. Okay. Here, these 4 instructions actually give you the same result, meaning R1 would equal 0. Same result. มองออกใช่ไหมทำไม R1 เป็น0 Clear it, you get 0. You move 0 to it, you also got 0. Right? Or you subtract with itself, that also give you 0. Or you exclusive OR with itself, that also give you 0. So technically speaking, it gives you the same result.
I see.
Question is, which one is faster?
I mean, something that seems to be swift for it. I would just say clear.
Your intuition would say, why don't use clear or else why would they give you the clear instructions?
Just like you said, it's so right. My intuition would say clear, but I saw.
Cheating? No. Next time, don't turn the slide.
What am I gonna do? I cannot just erase my memory like that.
Anyway, exclusive OR would give you the best performance for some reason.
Wow.
That means it is bad design in a sense, because your intuition would say, why don't just use clear? But it no longer true anyway, but back like 20 years ago for Intel processor, 4-bit exclusive OR, that's the fastest.
So it was like older machine, right?
So it depends anyway. But good compiler should give you a trade-off. Which one should I use? Which one would give me the better result, the fastest? Logically, they are the same.
My section.
But optimization matter here. Okay, let's try this.
Yeah, I think I can already see it. So why can't we just make like a single value where we already modify the certain years together?
Okay.
So why don't we like do it in paper and then just write down something like HS equal to.
Yeah, sure.
Be like,
Oh, what else? What else can we do?
A at index 99
yeah.
B equal A at index 99 divided by
99 or 100 in this case.
Yeah, I was just thinking, so we can divide H with you know, oh no, I mean like, we do D first. And then we divide everything by 24, and then we get H.
H and B are separate variables, so there are only the final result is needed. So at index 99 for A. So this one
Okay,
Oh.
got it?
I didn't know what, I didn't know.
Okay. Let me do it in the proper way that the compiler may do it, okay? First, these two instruction is invariant to the loop, meaning you run loop 1,000 times, it doesn't change anything. So we call it loop invariant. We would do code motion. Let's move it out. So we can do like HS equal, it's like this, DS equal, HS 24, it's an example, and then you go with the follow, whatever. So we move it up because it doesn't say it regardless of the loop, it's gonna do the same calculation. We call code motion loop invariant like that. But for this code, it's tricky in the sense that, oh, why do we need a loop? Because at the end of the day, if we only use H and D, that's basically A 100. Just the last value. So why do we need a loop? So we can just take the loop out. Because H and D also loop invariant in a sense, right? It's just the last loop that matters. Right? And if you want to do further optimization, you might get something like, oh, it's A 100 divided by what? 36,000. And if you do it more, you would say, oh, this is actually
A1.
H divided by 24, right?
Oh.
So you can also do copy propagation like optimize from loops to no loops and just two instructions.
Yes.
One example, maybe. Well, I can go with example like this all day. Okay, let's try this one. Let's try this one. This is the last one, I guess. Oh, two more. Okay. Try this one. Got it?
Oh, I see.
Uh-huh. A, you put it here. Then you propagate A and B down here. So what do you get? D equal what? B plus C minus what? B plus C plus C. And you get what? Minus C at the end of the day. Yeah, the copy propagation. This is the kind of thing that we call optimization. All right. Okay, let's try this one.ครับซันได้มีอะไรเปล่าอ๋อครับก็ยังไม่ได้เตรียมอะไรเป็นพิเศษแต่ก็คิดว่าคงจะเอาหลักสูตรมาเล่าแล้วก็บอกว่าหมายถึงว่าภาคมีหลักสูตรอะไรบ้างแล้วก็มีแนะนำพวกเรียนอะไรอ่ะทั้งแผนการวางแผนการศึกษาการลง individual study แล้วก็วิธีการเรียนต่ออะไรอย่างเงี้ยครับครับโอเคก็นั่นแหละแล้วพวกฝั่งกิจการนิสิตอาจารย์ได้ต้องพูดอะไรป่ะล่ะหรือจะเชิญใครมาพูดป่ะอืมงั้นก็ไม่มีอะไรได้ก็เล่นบทพิธีกรไปก็ได้ก็ฝากประมาณนั้นนะครับให้แนะนำเรื่องเรียนต่อเรื่องหลักสูตรอื่นๆอย่างนั้นนะครับก็กลายเป็น40 นาทีรวบไปครับครับนะครับโอเคเดี๋ยวทำเสร็จสไลด์แล้วเดี๋ยวแชร์ไปให้ดูอีกทีครับครับผมครับโอเค sorry got it basic alignment อ้าว A is 1 byte, short is 2 byte, this is 4 byte, this is 1 byte, this is long would be what? 32 bytes. Sorry. Long would be 8 bytes, and double would be 8 bytes. Okay. Right? Just if you don't know. I keep drawing things. So I make it 4 bytes per line, just to make it easier to draw it. It would, if we do elastic alignment, it would be A is go here. Right? And then B is 2 bytes must be divided by 2, so it go like this. And C would be 4 byte divided by 4 equals 0. D would go here. And E will go like this. Okay. And F, 8 byte. Yeah, you got the idea. Yeah, practice a little bit. You got the idea anyway. Yeah.
I want to be more than four, right?
Oh, you can write 8 columns per line for the current architecture, which is 64-bit, but I find that explain it in 32-bit is easier to understand. Okay. All right, we got few more minutes, so let me explain exercise number 1, and I call it a day for you. Stop screen sharing, and we go to this. Still here, okay. So I start. Yeah. Share screen here. All right, there we go. This will be the assignment. I make sure I post it today. Okay. You normally you've got about a week to do it, and we've got TA to do that. Well, basically, you need a compiler. Just get GCC. But if you use Windows and you don't have compiler, you can install Sigwin free compiler. If you use Mac, you can use Xcode command line, whatever you want. Just got a compiler, just like that. Once you got a compiler, let's write a simple hello world program, just to see that it works. If you use GCC, you can just compile hello world and run hello. If it works, if it gives you hello world, it's good. And we also need tools like disassembler. Again, I use free disassembler object dump. Or for Mac, you can use this or tools. It would give you some kind of assembly code, which might be Martian for you anyway, but that's the point of the assignment. I want you to make sense of it a little bit.
So what app do I have to go to install?
So I have little code here.
Yes.
Translate it to assembly. If you use GCC, just try GCC minus S, capital S. It would give you assembly code. And explain to me how does it work. Is it restrict alignment or unrestrict alignment from the code that you got? And then you turn on some optimization, level 1, level 2, level 3. So I got a few codes that I want you to do optimization. Basically GCC minus turn on optimization level 0, 1, 2, 3, like that. And do the timer to measure the speed of the code. Do the analysis, just like that. Let me quickly show you something here. Okay. Quick demonstration. Okay, I just cut and paste this code a little bit. Okay. And this is the result that you get when you compile program. Rather than ask it to give you a binary executable program, you ask it to give you the assembly code. This is the assembly code. So make sense of it for me. You think from the code, is it restricted alignment or unrestricted alignment? How to tell? And if you turn on optimization, what is the difference? How to turn on optimization? You say, like optimization number 3 minus all 3 optimize. You will see different code when you do optimization. See, much shorter. Okay, this is without optimization. Wow, quite long. Once I do the optimization, quite short. So what kind of optimization happened when the compiler, what the compiler have done for me? If you can name the technique that compiler used, that's good. If not, just tell me, what do you see? Just want you to make sense about the technology a little bit. Okay, again, we only got about 3 or 6 hours that you learn about compiler and instruction set. I do not expect you to be expert, but at least you should be able to make sense of this. Yeah. So that's the assignment. Okay, any question? Are you hungry now? Or you got bad appetite from the lectures? That's another thing. Okay, if you have no more questions, I see you next week. We're gonna start a new chapter, which is more challenging. And don't forget, you have about 1 week to do the assignment. The TA would help with the grading. Okay, we will post that later. Okay. All right, that's it. Thank you. See you next week.